Internal loads. By the end of this section, you should be able to create the correct free body diagrams for internally cut systems in 2 dimensions and 3 dimensions, and in the free body diagrams, use the standard convention for the directions of normal forces and torsions. Then, using these free body diagrams, you should be able to create the equilibrium equations to solve for the 3 internal loads in 2 dimensions and the 6 internal loads in 3 dimensions. In this section, we are shifting our focus from external loads to internal loads. Up until now, we've looked at external forces and external moments that were acting on our structures, with the exception of truss analysis, where there we were looking at the internal forces in the members that made up the truss. But now we're going to extend that internal analysis beyond just the truss. In a truss, things were simple because all of the members that made up the truss were 2 force members, and we knew that the internal force in those members was only directed along the axis of the member itself. In general, the internal loads are not only acting along the axis of the member, and that's what we're going to be seeing in this section. So what we're really looking at are what are the loads that are holding the material together in our structure. And this is going to act as a bridge between what we're doing in statics and what we're doing in the follow-up course strength of materials, where in strength of materials, we're really focused on what's happening internal to the material itself. We're going to be using these internal loads we're finding to calculate the stresses in our material, and that is what is going to be causing a material to fail, is when the stress in the material is too high. And what you're going to see in the follow-up course is that every problem is really going to start with a statics problem, finding the external supports, then finding internal forces, and then using those internal forces further to do calculations. So the generalizations we're going to be making is that unlike members that make up a truss, the internal load is not strictly along the axis of the member. We cannot assume there is no internal moment in our members. And the load through the length of the member can be changing, unlike in a truss, where the internal load throughout the entire member was constant. So what does it look like when we are analyzing the internal loading? So if we have our beam, we are going to be interested in usually first solving the, in this case, 2D rigid body equilibrium problem. We want to know what's happening at the wall. What are the forces, what is the couple that the wall is exerting on our beam? But now the question is going to become not only what is happening at that support, but what's happening inside the beam itself. So in this example, we are looking at what are the internal forces at this point B, or at this AA section in the material. So in the external free body diagram, we can't see what's happening inside the material. It's all internal to that diagram. So what we have to do is make an internal cut through our material, and now it's going to expose the loads that were holding the material together. So this is pretty similar to what we did when we took section cuts in trusses, except there we only saw an internal normal force for a truss member because it was a 2-force member. Now we see a more general type of loading inside of our members. So if we see here on the right, we have 2 halves of this internal cut, which again is akin to a section cut. So if we take everything to the left of this AA section, this is what our internal free body diagram looks like. And if we take everything to the right of that section cut, then this is what our free body diagram would look like. So notice there are now 3 unknown loads introduced at that cut surface. And for here, I put a subscript B for these 3 unknown loads, because if we cut at point B versus somewhere to the right of it or somewhere to the left of it, these 3 loadings can be different and are subject to change depending on where we are analyzing the internal loading. So again, generally for these 2D rigid bodies, when we make this cut, we're going to be exposing 3 internal loads. And we're going to see when we get into 3D that it's going to introduce 6 internal loads. We also want to note from this picture that the directions of these loads are opposite in the opposite pictures. So in the left picture, I have this PB, which I'll explain what it is on the next section, to the right, but in the other half of the picture, it's to the left. VB down in the left picture, VB up in the right picture. MB counterclockwise in the left, M sub B clockwise in the right picture. So it's going to be a similar idea to what we saw here in the frames and machines. When we had both sides of connected members, we had to assume equal and opposite directions in the two pictures that those loads were present in.